All right, this is squeeze theorem, and so I'm going to explain what's going on first and then explain the definition. So we have a function h here and a function f, and we're looking at a little tiny picture of them so they could come over and do randomly weird stuff over here. We don't care. We're looking at it only at the value a, and they both are approaching the value L. You can see that coming in from the left and the right, they both approach the same thing. There's like a little squeeze there. So anything coming in here now is being squeezed. So if we have some function g, it's just being squeezed in between it. And how we write that then is that h is bigger than g and f is smaller than g. So if the limit as of f and h are both the same, since g has been squeezed in between them, g also has to have that limit as x approaches a. So we have f of x and h of x. H of x is bigger than f and g. F is smaller than g and h. And we end up with this nice little inequality. If this is true, where x is near a, so just that tiny little picture, and that the limit of h and the limit of f approach the same value, which is L, then the limit as x approaches a of g of x is equal to L. So this is how we use it. We start with an inequality that we know is true. So 2x is less than g of x, which is less than x squared. And we're going to find this limit of as x approaches 2 of g of x. So if we can show that the left, our f, and the right, our h, both approach the same number, that means g has to work the same way. So let's start with the bottom one. We'll call this one f, and we'll call this one h so it matches above. So the limit as x approaches 2 of our 2x, that would be 4. And the limit as x approaches 2 of x squared is also equal to 4. So the limit as x approaches 2 of 2x is equal to the limit as x approaches 2 of x squared, which is equal to 4. You can now say by the squeeze theorem, therefore, the limit as x approaches 2 of g of x, which has been squeezed by f and h, is also equal to 4. So if you set up an inequality, one that has a value that's always less and one that's bigger than g within that little tiny area of 2, then all you have to do is show that those two equal the same thing and g has to approach that same value. So like here, let's look at this one. So we can see that if you plugged in 0, we get a d and e for sine over 1 over x. But let's try squeeze theorem on it and see what happens. So what inequality do you know that deals with sine? Well, sine is between -1 and 1. And so we can just start there. And we're going to take this now and modify it into that. So if we take this, we have to have something we start with. This is 100% true. And so now if we multiply all the sides by x, we end up with, x squared, we end up with this. So by putting an x squared on there, it's not going to change anything. It's like multiplying everything by 3 or 4 or 5. Even if we put in an x, the inequalities would flip, giving us something that's the same. But we have a nice positive here because it's x squared, so it's always going to work. Now we have our inequality. This is 100% true because this is true, and we just use normal properties. So now we can say, what is the limit as x approaches 0 of -x squared? That's 0. And what is the limit as x approaches 0 of x squared? That's also 0. Therefore, which we should probably finish it. So the limit as x approaches 0 of -x squared is equal to the limit as x approaches 0 of x squared, which is 0. Therefore, with the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x also has to equal 0. And if we look at the calculator, you can see that there's no value there, but scrolling to the left and the right, they are approaching 0, so it verifies what we were looking for. So that's our limit. So now I want you to try this problem. Hit pause and give it a shot. And here you go. So now what you have to make sure is that if you're using squeeze theorem, that you are writing every single part of it. We're making our inequality. That is 100% true. We're now saying that the limit of this one is equal to the limit of that one, which is equal to L. See, we're writing each part. So we had part 1, part 2, and then we finish with our limit. So this and this both have to be true to show that. So as you go through them, you are showing that this is true, this is true, therefore this is true. So you're always showing 1, 2 to get our answer. So 1, 2, and there's our answer. So we know this is true because we've shown it. And then we know this is true because we've figured it out. And because that is true and that is true, that is true. Now this last one, you don't have to do anything. You could have just plugged in 0 and you would have got 0. But there you go.